number that we see a lot of the times when we're working with quadratics or other types of functions that we're going to see in this course. These numbers are known as radical numbers. Radical numbers are also known as irrational numbers. In math, we have two types of numbers that are called rational numbers or irrational numbers. A rational number is a number which is definitive. It is either a whole number or a decimal which has some decimal places but it ends. An irrational number is completely different. It's not a whole number. It's a type of decimal number, but a decimal number where there is no repetition in the decimal places. It goes on forever and has no pattern. We know of some irrational numbers already, like the number pi, 3.14159, which keeps going on forever and ever. There's another irrational number you're going to learn about. That's the number e. And there's a bunch of other irrational numbers that you'll discover. But a common type of irrational number that we see are these radical numbers, or numbers that are found underneath a square root sign, which we call a radical sign. A radical number is a number that is underneath a radical sign where the number underneath is not a perfect square, meaning the square root of 9 would not be a radical number or an irrational number because we know the square root of 9 is 3. But the square root of 8 is not a perfect square, so the square root of 8 would end up being an irrational number. This number underneath the radical sign we call the radicand. Just like when working with fractions or any other types of mathematics, we like to always know how to simplify or properly simplify our answers. So in today's lesson, we're going to look at how do you properly simplify radical numbers. And we're also going to look at how you operate with radical numbers. Are they the same, or are there some differences between radical numbers and just normal whole numbers or fractions or decimals? We're going to look at some examples of those. A couple of other important terms you're going to need to know prior to us working with radical numbers. A question might ask you to find an answer as an approximate value. And in this case, we would take our final answer of whatever radical number we come up with and throw that into our calculator and find an answer rounded to 1 or 2 decimal places. But if we're asked to leave our solution in an exact value, or if we have to operate with our answer at a different time or a bit later in the question, we would want to leave it as a radical number. So we need to know how to properly simplify. So let's go over the basics. The first rule of simplifying is one that's very easy. A radical number can always be split into two radical numbers that multiply together, where the two radicands of those radical numbers multiplied to whatever the radicand was of the original number. The easiest way to think of that is if you start with one number as a radical number, you can split it into two other radical numbers where both numbers underneath the square root sign multiplied to that first number. But we don't want to pick any two numbers. We want to make sure that one of the two numbers that we pick is a perfect square. Remember, a perfect square is a number in which if we square root it, will become a whole number. So let's look at the example here, the square root of 50. The square root of 50 is a radical number, but if we took the square root of 50 and put it in a calculator, it would end up being a decimal answer that never ends. So we want to simplify this as best as possible. To do that, we want to find two numbers in which we can split it. These two numbers we're going to make into two radical numbers, but one of these radical numbers we want to be a perfect square. So can you think of two numbers that multiply to 50 where one of them is a perfect square? It might be handy to write out some examples of perfect squares off to the side just so you get used to them. So numbers like 4 or 9, 16, 25, 36, and so on, all of these are perfect squares. Well, the square root of 50, I think we can easily see that it can be split up into the square root of 25 and the square root of 2. Notice how 25 times 2 is 50. So when we write this out, we always write the perfect square radical number first, and then the part that isn't a perfect square second. So now we're going to rewrite this as if we can square root the 25, which we can. So the square root of 25 is 5, and because we can't square root 2, we're just going to leave it as a radical number the square root of 2, which leaves us with the simplified answer of 5 times the square root of 2, or we would just say 5 root 2. Here's another example. Let's try to simplify the square root of 180. We're going to need to find two numbers that multiply to 180, where one of them is a perfect square. 180 is a bit bigger of a number, so it's going to be a bit harder to find. But the important thing here is that we can't just split this into two random numbers. I can't just say that this equals the square root of 18 times the square root of 10. I mean, although that is true, this will not help us simplify this, as neither of those are perfect squares. So we don't want to do that action. We need to make sure that our two numbers have one, which is a perfect square. So if we look at our numbers here, we can see that 180 is divisible by 18, because it's 18 times 10, we just said that. And I know 18 is divisible by 9. So I know that 9 will go into 180. In fact, it goes in 20 times. So we can change this into the square root of 9. Remember, I want to write the perfect square first, times the square root of 20. And we know the square root of 9 is 3. So this will just equal 3 times the square root of 20, or we would say 3 root 20. So we just did one step here to simplify. But look at the square root of 20. Can we simplify that number further? Well, looking at our perfect squares, the number 4 can also multiply into 20, and 4 is a perfect square. So we can now rewrite the square root of 20, keep that 3 there, as the square root of 4 times the square root of 5. 4 times 5 equals 20. And since 4 is a perfect square, we're going to rewrite this as 3 multiplied by the square root of 4, which is 2, multiplied by 5, and 3 times 2 is 6, so this ends up being 6 root 5. 6 root 5 and the square root of 180 have the same value. If you plug both of them into your calculator, you get the same number. But this is the more simplified version. Now that took 4 different steps in order to properly simplify. But if you can find the biggest perfect square that can go into your original answer, you can reduce the number of steps it would take in order to solve. Here's how. Notice how the square root of 180 could also be split into two numbers where one of those numbers is 36. 36 times 5 happens to also equal 180. Well, the square root of 36 is 6, so we can see here that this ends up being 6 times the square root of 5, or 6 root 5, which is exactly what we had before. So again, both will get you to the right spot. Just remember to double check these numbers again, so once you do it once, you may need to simplify it again afterwards. Not only can we simplify radical numbers themselves, but we can also operate using radical numbers. And they work just like if we were going to add or subtract variables, or multiply or divide variables. So for instance, if we had 3x plus 6x, well, 3x's plus 6x's give us a total of 9x's. The same thing works with radical numbers. If you had 3 root 5's, and then you added another 6 root 5's to that pile, now you would have a total pile of 9 root 5's. You treat root 5 like a variable, or like a certain type, or a like term. So we're going to operate with radical numbers just like we would with variables. But here's the thing to remember. If we had x's and x's, we can add them together. But we can't add x's and y's together. They're not like terms. Same rules apply with radical numbers. A root 5 can add with a root 5, but a root 5 can't add with, say, a root 7. Those are not like terms, so those are not able to add together. Here are a couple of examples to try. 4 root 3 subtract 2 root 27. Well, root 3 itself cannot be simplified further. There's no other number that can multiply into 3 where one's a perfect square. So as it stands right now, this cannot be subtracted because we don't have like terms. But the square root of 27 can be simplified further. So let's rewrite this 4 root 3 out first and figure out what two numbers can multiply to 27. Well, 27 is divisible by 9. We know 9 is a perfect square. So I'm going to write this as subtract 2, which was already there, times the square root of 9 times the square root of 3, 9 times 3 being 27. And we know the square root of 9 is 3. So this is going to be 4 root 3 subtract 2 times the square root of 9, which is 3. So 2 times 3 is 6, and this root 3 is still here. And now look what we have. 4 root 3 subtract 6 root 3. Those are now like terms, both of them having root 3's. So we can subtract them. 4 subtract 6 is negative 2. So this would end up being negative 2 root 3's, or negative 2 root 3. Okay, let's do another one. 5 root 8 plus 3 root 18. Again, not currently like terms, so let's try to simplify these before we add them together. Root 8 can be split into root 4 and root 2, where root 4 is our perfect square. And 18, we've seen 18 before. We know that 18 is divisible by 9, so we can split 18 into root 9 root 2, because 9 times 2 is 18. And we know the square root of 4 is 2, so 5 times 2 is 10, so that's 10 root 2. And 3 times the square root of 9 is 3, so 3 times 3 is 9, so this is going to be plus 9 root 2. And 10 root 2's plus 9 root 2's is 19 root 2's, or 19 root 2 is our final simplified answer. The last bit of simplifying we're going to look at is when we want to multiply radical numbers. Again, this works just like if we're multiplying numbers with variables. We would multiply coefficients times coefficients and a variable times a variable. In this case, we're going to multiply a radical times a radical. So 2 root 3 multiplied to 3 root 6, well, the coefficient 2 is going to multiply with the coefficient 3, and the radical number root 3 is going to multiply with the radical number root 6. So we end up here with 2 times 3 is 6, root 3 times root 6. Remember, the rule here is when we multiply radical numbers, you can just get one radical number where you multiply the radicands, or the number underneath the square root sign. So 3 times 6 is 18. But we do have to double check to see if this root 18 can be simplified, and it can. Remember, it's root 9 root 2. So this turns into 6 times root 9 times root 2, and root 9 again being 3. So 6 times 3 is 18 times the square root of 2, or 18 root 2. We have an example where we have one radical number multiplied to two terms inside a bracket. And just like we would with normal numbers, we will distribute through. So the radical number out front will multiply to the 4, and then it'll multiply to the 5 root 3. So 2 root 3 multiplied by 4, remembering that only coefficients multiply with coefficients, so 2 times 4 is 8. The root 3 doesn't multiply with anything else, so it stays as just root 3. And then we have 2 root 3 times 5 root 3. 2 times 5 is 10, so positive 10 or plus 10. And root 3 times root 3 is root 9. But we have a weird or an interesting situation where we have a radical number times itself. It's like root 3 times root 3. Well, that would equal root 9, but we know root 9 equals 3. So this brings up an interesting point here where anytime we have a radical number with, let's say, a radicand n, and we multiply it by itself, so another radical number multiplied by radicand n, this will equal just n without the radical number sign. So root 9 is equal to 3. 10 times 3 is 30, so we end up here with 8 root 3 plus 10 times 3 is 30. Okay, one bonus example to leave you with. What happens when we have a binomial times a binomial? Well, we've seen before that we would use FOIL, right? First outside, inside last, or double distribution. So we're going to do the same thing here. Root 3 times 2. Root 3 times 2, well, 2 is a coefficient or whole number. Root 3 is our radical number. So this just equals 2 root 3. Those numbers can't actually multiply to each other because they're different sorts of things. Root 3 times negative root 3. Well, we have that situation where we're multiplying a radical number by the same number. So we know that's just going to equal negative root 9, which is 3, so negative 3. Then we have 5 times 2. 5 times 2 is 10, positive 10. And 5 times negative root 3 is negative 5 root 3. We'll collect some like terms here. So 2 root 3's subtract 5 root 3's. Well, that gives us negative 3 root 3's. And negative 3 plus 10 is 7. So we can write this as negative 3 root 3 plus 7. Or maybe to get rid of some of these signs that we don't necessarily need, we'll put it in a different order. So 7 minus 3 root 3. Either answer is acceptable. This one just looks a little nicer. And there you have it. That is how you simplify radical numbers. So don't forget, when you have an answer that has a radical number inside of it, especially when working with quadratics, remember to try to simplify that radical number so that you can get full marks.